the last of module 4. Okay. Last two classes we discussed symmetrical components and sequence networks. Okay. Last class we discussed symmetrical components and sequence networks. What is the use of symmetrical components? Why they are used? Suryamani, talk. Why symmetrical components are used? Anyone? You? Why symmetrical components are used? Why we discuss symmetrical components? Look at that. What is the utility of symmetrical components? Okay. So for unsymmetrical faults, the phases are not balanced and therefore you cannot convert that to a single phase network. So what is the alternative? So one alternative is to go for the three phase analysis. Find out the current in each phases, voltages, etc., which is very complicated. Or the alternative is converting the network into three separate balanced systems and interconnect them. Okay. Now symmetrical components is the theory behind that. It says that, as we discussed in that class, symmetrical component says that any voltage or current, or in fact any vector quantity, can be considered to be a summation of a positive sequence, a negative sequence and a zero sequence. Okay? Right? So therefore any balanced system also can be converted into a positive sequence, negative sequence as well as zero sequence. No problem. But the same answer you will get by doing a single phase analysis. Okay? Now the concept of symmetrical component leads to sequence networks. The concept of symmetrical components lead to sequence networks. Okay? We have seen that in the last class. Especially we deal with three kinds of components: generators, transmission lines, transformers. Right? What about the sequence network of a transmission line? What we found out in the last class, that positive and negative sequences are equal for a transmission line. And zero sequence network is some formula, I think. Zs plus 3 Zl or 2 Zl. Okay. Then for generators, positive and negative sequences networks are same, but in the negative sequence there is no voltage source because the generated voltage is always positive sequence. Okay. That is the meaning of negative sequence voltage. Okay. Because when we take the voltage from the terminals, irrespective of whatever be the direction of the rotating magnetic field, we take it as a positive voltage. So positive sequence network means the voltage source will be there. In a negative sequence network, there will be no voltage source. Otherwise, it is the same. Zero sequence network will depend on the availability of neutral connection and all those things. Okay. Now, the interesting case is the transformer. For the transformer, the positive and negative sequence reactances are nothing but the leakage reactance. Why? Leakage reactance means what? It is the transformer reactance. So positive, negative are both same as the transformer reactance. Why? For generators it is different, but for transformers it is the same. Why? Because it is not a rotary machine. It's a static device. But the problem comes with the zero sequence network, because you might have read about three-phase transformers. Okay, so we can have star delta, delta delta, star star, and on the top of that the star point can be grounded, it may not be grounded. So depending on this connection, we have several zero sequence networks of the transformers that we discussed in the last class. Okay. So today's topic, the computation of unsymmetrical faults, eventually it is the summary of the last two classes. That means for any fault situation, we will see how the sequence networks are connected to compute the fault current. So how many faults you know? Unsymmetrical faults, the most popular one, line to ground, line to line, double line to ground. So we will have three connections corresponding to this faults, and then you will see how the fault current will be calculated. Okay. So this is the summary that we have been talking about till now. Broadly speaking, the faults can be classified as shunt faults and series faults. Shunt type faults involve power conductor or conductors to ground, whereas or short circuit between the conductors, line to line fault. When circuits are controlled by fuses or any device which does not open all the three phases, one or two phases of the circuit may be opened while other phase remains closed. This is called a series type of fault. It's making broken conductors. Shunt faults are characterized by increase in current and fall in voltage and frequency, whereas series faults are characterized by increase in voltage. Remember the difference. Okay? Somewhere it might be asked. Okay. And fall in current in the voltage phase. Shunt faults are classified as line to ground, line to line, double line to ground, and three-phase fault. Of these, the first three are unsymmetrical faults, as the symmetry is disturbed in one of the phases. Okay, because the fault occurs in one phase, line to ground. The other two will be unbalanced. Three-phase fault is a balanced fault. So every textbook you can find out. This is a typical generator. Okay. So when we say fault on the transmission line, it is actually a fault on the generator terminals, because generators are connected to the transmission lines. So this is a what kind of fault? Line to ground fault. Only one line, phase A we have shown. Okay, line to ground fault. This open means doesn't mean that it is open. Okay. Some load is connected. Now under this condition, when the current is flowing, if a line to ground fault occurs, in that case how are you going to analyze this? So during line to ground fault, the positive sequence network, the negative sequence network, and the zero sequence network, they are connected in series. Okay? So you know the voltage before the fault, pre-fault voltage, and you have a series connection of the various impedances. Wherefrom you will get Z1, Z2 and Z0, positive, negative and zero sequence. Wherefrom you will get from generator nameplate. Okay, it can also be obtained experimentally, the positive, negative and zero sequence impedance. Okay. So draw this equivalent network, all of you. Draw the network. Okay, this is clear. Now we'll see why it is so. Why we connect the three networks in series. So this is the analysis of the fault. The network on the left side, no need to write, the network on the left side that you saw. Okay. Since the fault takes on phase A, okay, VA is 0, IB and IC are also 0, unloaded. We are considering, suppose, unloaded. IB and IC will be 0 because the fault is occurring on the A phase only. Okay. Sequence network equations are, this is from the lesson 22, symmetrical components and symmetrical component equation. Okay. So the positive sequence voltage will be EA minus IA1 minus Z1. Why is so? Because the voltage is only positive sequence. There is nothing called a negative sequence voltage. That can be negative sequence current, but no negative sequence voltage. Okay. Okay. Then VA2 is minus IA to Z2. Because there are no voltages in the zero sequence and negative sequence networks. And therefore, simplifying, we find each sequence current to be IA by 3. Okay, then we find out the voltage is made to be 0 and we substitute. Eventually, we write out this equation only. Eventually, the fault current is given by EA divided by Z1 plus Z2 plus Z2. Okay, this derivation is not important for you. Only for reference it is given. Any textbook it will be provided. But for you, what is important is this. IA1 is equal to default voltage divided by positive sequence, negative sequence, and negative sequence values. So if you are given this value, you can easily find out the fault current due for a line to ground. Okay, that is what you need to remember. This derivation is mostly applicable to the PG students. But at your level, you should know what formula to apply when there is a line to ground. The next is, so you saw that for a line to ground fault, this is the equivalent circuit, which is a summation of positive, negative and zero sequence. No need to draw the second one, or you draw it. See, in this case, there is a line to line fault between B and C, and this is the equivalent network. This is the equivalent network. So for this fault, this will be the equivalent network. Derivation has skipped. Okay, it's not required for you. So what is important is you just mention line to line fault. Write down line to line fault, and then write this equation. No need to draw the network. No need to draw this network because it is written here. The fault is between line D and C. So for you, this is important. Okay. This is the equivalent network for this fault, which is also again a combination of positive, negative, and zero sequence networks. Will there be any zero sequence impedance involved here? Because it is line to line. It's a line to line fault. Where there is no involvement of ground, there will be no zero sequence impedance involved. Okay? So that's why you don't have a zero sequence impedance here. There is no zero sequence impedance, only the fault impedance. So if there is some fault impedance here, which is 0 of course, in this case it is 0, ZF is 0 here. Clear? Next one is line to line fault. I think somehow it is okay. The derivation somehow it is there, it's not so. Anyway, okay. So this is, you need not write, just note. Earlier case we considered a solid fault. What do you mean by a solid fault? When the ground, the fault when it is connected to ground, in between there is no impedance. Okay, it's a solid fault. It's a solid conductor type. Okay. Whereas if you have a ground fault impedance ZF, then the network will become like this. So if the problem involves ground fault impedance, you need to use this equivalent circuits. Okay? No need to draw. Next point is double line to ground fault. Okay? This is a little bit complicated. So draw this circuit. Single line to double line to ground fault. So here what has happened? So there is a fault between these two lines, but that fault is again connected to the ground to a impedance ZF. ZF may be 0. Okay. So draw this. This is a typical case of double line to ground fault. Okay. So for this double line to ground fault, this will be the equivalent circuit. Okay. Now this involves zero sequence impedance. Why? Groundage, because there is a ground connection. So when there is a ground connection, zero sequence impedance will be there. If there is no ground connection, no zero sequence impedance. Okay, that we discussed in the very first sequence networks. Okay. So here you see there is a 3 ZF also, but then many times ZF is 0. So in that case, this will be 0. Okay. And this network is eventually this formula. This network is, if you see this closely, it is converted into this formula. Okay. Z2 means not Z square, it is negative sequence. This is positive sequence. One, here in this book, I have taken it from the Hardware book. So in this book, superscript 1 means positive sequence network impedance, superscript 2 means negative sequence, 0 means zero sequence. Okay. So we'll solve a problem. What you have understood so far? Symmetrical, the concept of symmetrical components is the principle behind all this, which says that any vector can be represented by means of a positive sequence, a negative sequence, and a zero sequence vector. That is the principle. Okay, it's a mathematical principle. It is proved that whatever power is calculated using normal vectors will be the same when we calculate that using sequence vectors. That proof is there in lesson 22 last slide. It might be asked sometimes, 2 mark question. Okay, prove the power invariance for sequence symmetrical components. Okay, done. Based on the symmetrical components, we develop sequence networks for various components of the power systems. Okay. Now, what is the purpose? To compute the fault current during unsymmetrical faults. Okay. What we do? Based on the nature of the fault, in line to ground, line to line, and double line to ground, we get a particular topology. Topology means the circuit. So based on the topology, we make the derivation, and eventually we get one equivalent circuit involving all the 3 types of networks except line to line fault, which does not involve the zero sequence network. Okay. So when you are given a problem to compute the fault current, nobody will ask you the derivation. If you in the exam, you may be asked to compute the unsymmetrical fault current. So in that case, you have to remember these 3 networks only and the formulas. That's it. So now we will see the application. The first part was symmetrical fault computation. Next, sequence network related problems. So we will see the first problem only. Okay. Every textbook has some problem. Just try to mention the ratings. 30 MVA, 13.8 kV, 3-phase alternate. Mention the ratings. MVA, 13.8 kV, 3-phase alternate. Okay. Subtransient reactance 0.1 per unit. Okay. Negative and zero sequence 0.15 per unit, 0.05 per unit. 5% means 0.05 per unit. Okay. I subtransient kind of. Why we are taking subtransient? I have already answered. I am again. Subtransient current impedance kind of. Because that is the impedance the alternator offers during the initial time of the fault. Okay. The transformer supplies 2 motors. Alternator supplies 2 motors over a transmission line and transformers. The motors have rating of, just mention the ratings. No need to write in detail. Motors are 20 MVA, 10 MVA, 20 MVA, 10 MVA. and both having 12.5 kV rating. Mention the ratings. And their subtraction reactance is 20% and negative zero sequence 20 and 5%. Then there is a current limiting reactor 2 ohm. Okay, in the neutral of the alternator. That means ZF is equal to 2 ohm. It is given. Okay, fault impedance is given because there is a current limiting reactor. The three-phase transformers are of this rating with leakage reactance of 10%. Okay, that means positive and negative sequence reactance is 0.01 per unit. Okay. Zero sequence reactance is 200 ohm. Okay. Zero sequence reactance is 200 ohm. So for this problem, compute line to ground, line to line, and double line to ground fault currents. Assume pre-fault voltage to be 120 kV, which is less than the 13.8 kV, right? 120 volts. We'll see in the problem. We'll see how much it is taken. Very high. 120 kV is very high. I think 120 kV on the transmission line side. Yes, this 120 kV is on the transmission line side because you see 13.2 115 kV. So what is the rated voltage on the transmission line side? 13.8 into 115 by 13.2. Right? So around 120 kV. That is the rated voltage on the transmission line side. And that is what at rated voltage. That means the fault is occurring at the rated voltage on the transmission line side. Okay. Now this network is this one. Draw this. Okay. So this is shown like a resistance. Okay. But generator side has a current limiting reactor. For this system, it is asked compute the current for line to ground fault, line to line fault, double line to ground fault. So what will be your first step? First is converting all the impedances into one base. Okay, both on the transmission line side as well as the generator side. That's the first step. Convert everything into one base. Then draw the reactance diagram based on the nature of the fault. Okay. So what are the steps? Step 1 will be convert to one common base. Step 2, reactance diagram. And step 3 is computation using the given formula. Computation using the given or relevant formula. Relevant formula means we have written 3 formulas. One for line to ground, one for line to line, one for double line to ground. You have to directly use this formula. That's it. Okay. So we'll see the solution. So you attempt this at your home in detail. Use calculator because in exam similar questions might be asked 8 marks. Okay. If this question will be asked, two faults will be asked at most. If one fault current is asked, LG only 4 marks. Okay. If 2 faults, 8 marks. Okay. So first you need to find out all the parameters on a single base, which is done here. Okay. How to convert the impedance from one base to another base? Z new by Z old is equal to MVA new by MVA old into KV old by KV new square, right? So accordingly, these formulas have been used. Okay. Same for the motors. Now this is the sequence network for the which fault? Line to ground fault. Because positive negative and zero sequence networks are connected in series. The positive sequence network has EMF. Same value as the positive sequence network, no EMF in negative sequence. Zero sequence network is like this because it is a star grounded connection on the generator side and delta connection on the transformer side. Why this connection is like this? For that you have to refer back to lesson 23. It is given for different type of connections. If the connection is like this, delta star grounded and star grounded delta, in that case what zero sequence network you are going to use? That is given in the previous lesson. Okay, refer to. Okay, then you will simplify this and compute line to ground. Okay. Next, for line to line fault, this is the formula that you have used. Okay, I think current limiting reactor doesn't apply here because there is no connection to ground, no zero sequence. So only Z1 plus Z2. And in the last case, you are going to use that parallel formula, okay, and find out the fault. Okay. So this you have to practice yourself. Only one example if you practice, you can solve any problem that will be asked. Okay. So in this way you stop.